Okay, what I just want to talk about is something Alan looked at the other day, and something that was new, which was called partial fractions. Now, the idea of partial fractions is really just to be able to break up a fraction into two separate fractions. So I'm just going to use the example here of looking at something like 5, 6, and if we want to break it up into some number on 2 and plus some number on 3. So it's really just like the reversal of adding two fractions. So it's decomposing a fraction that we've already put together from two other ones. Now this is necessary to do some of the integration because we can't do with some of the denominators we can't start to integrate easily, so we need to break them apart. So the idea here is, so just do our normal work with fractions and get the common denominator from a on 2 plus b on 3, and we get the 3a plus 2b on 6. Now, because I got my denominators the same, the numerators must be the same here, so that's where we get 5 is equal to 3a plus 2b. Now, when we look at this, we can see that there's infinite number of solutions to 3a plus 2b. But an obvious one is a is equal to 1 and b is equal to 1. So 5, 6 equals 1 half plus 1/3. So like we could break this up a number of ways. That's not always the case when we deal with polynomials. So let's have a look at something like 4 on x times x1, x plus 1. We want to break it up. See how we want to break it up in two forms here. Something on x plus some number on x plus 1. What I should say about partial fractions as well is that I shouldn't be able to do any division between our numerator here and our denominator. The denominator should be of a degree that's higher than the numerator. So you can't actually, if it's the numerator's got a higher degree, we can do some polynomial division. But this is not going to be the case in the questions we're doing. So you can see the degree of 4 is 0 and the degree of the denominator here is squared. So that's not a problem. So our process is to make these two equal in this line. So we've got the a on x and the b on x plus 1. But then we start to look at it and put them as a common denominator. So we get our two denominators being the same, which means our numerators must be equal. So there's two ways to do it. I'll go through both ways of doing this. So I'm just going to ignore the denominators and just work with the numerators in this line. So I've just got the 4 is equal to ax plus 1 plus bx. Now the first way to do it is just to keep going and simplify these and collect the terms. So we've got a plus b times x plus a when we've manipulated our algebra. So if that's the case, notice this one, I've got just a 4 here, but really it's 0x plus 4. So that means what's the coefficient of x? It must be equal to the coefficient of x on both sides. So a plus b must be equal to 0, and the constant must be equal to whatever constant we've got there, which makes it easy because that means a is equal to 4. And if a plus b is equal to 0, that implies that b must be equal to minus 4. So I get my values for a and b. Another way to do it, and you can use either way to find that, is to, again, have our line here, 4 is equal to ax plus 1 plus bx, and just start substituting any value in for x. Now you can throw any value you want. I start to use 0 because that starts to cancel that term out. So that just gives me a outside of 0 plus 1, so a would be equal to 4. And then I'll usually sometimes let x be equal to 1 or minus 1. Minus 1 probably would have been a little bit better in this case because it would have cancelled out the first one there with a. But that's okay. And it wasn't a hard equation to solve. And I come down to b is equal to minus 4. So that allows us to now to get this fraction of 4 over x plus times x plus 1, which would be the same as 4 on x minus 4 on x plus 1. We can't integrate that, but we can integrate that one and we can integrate that one. They both work out as log functions. So that's why we're going to be looking at and use partial fractions at times just to help solve integration problems.